Hello, so today we're going to try to derive the Schrödinger equation. So we're going to be deriving the time-independent Schrödinger equation, and then from there we're going to derive the time-dependent Schrödinger equation. So first of all, let's start with things you should know. So you should know that energy is equal to kinetic energy plus potential energy. You should know that the quantum operator for momentum is equal to IH bar multiplied by the gradient. You should know what the gradient is. The gradient is the differentiation of the wave function with respect to the x dimension plus the differentiation of the wave function with respect to the y dimension plus the differentiation of the wave function plus over with respect to the z dimension. Apart from that, you should know that the energy could be written as HF. You should also know that the Hamiltonian operator is equal to energy, which is equal to kinetic energy plus potential energy. Okay, so we're gonna be adding a couple of more things as we go, but I'll describe them later on. So first of all, let's start classically. H is equal to kinetic energy plus potential energy. Let's add one more thing here. Kinetic energy is equal to half of the mass multiplied by the velocity squared, which is equal to the momentum squared over 2m. We're going to be using this form for the time being. So H is equal to p squared over 2m plus v, because v is basically the potential energy term in terms of the electromagnetic. So it's basically electromagnetic potential energy. It depends on where the electron is. Okay, so this is classical mechanics. We want to move on to quantum mechanics because the Schrödinger equation describes quantum mechanics, the wave function, which is a quantum mechanical function. So let's replace p with a little hat, the momentum operator. So I h bar multiplied by the gradient, all of it squared, over 2m plus v. So now let's square it. We get that minus, because I is the square root of minus 1, so the square is minus 1, minus h bar squared over 2m multiplied by the gradient squared. An important thing to know is that the square of the gradient is basically this term, but the second order derivative for everything. it's called the Laplacian. So the gradient is this, and then once you square it, it's called the Laplacian operator, plus v. And remember that we said that energy is equal to the Hamiltonian. So let's write it here. Minus h bar squared over 2m multiplied by the Laplacian term plus v is equal to the energy. But this is quantum mechanics, and the whole point of quantum mechanics is that not everything is discrete. Not everything. Everything is discrete. Sorry. Everything's discrete. Oh my god. Okay. Thank God this is not the official one. So I'm gonna. Okay. So you need a function to determine the wave properties. So that's called the wave function. Let's add it here. It's denoted by psi. It's equal to e to the I kx minus omega t, where k is equal to 2 pi over the wavelength. It's basically the wavelength vector, and omega is equal to 2 pi multiplied by the frequency. Okay, so now let's quantize this by multiplying it by the wave function. 2m squared plus v, all of it into the wave function, equal to energy. But whatever we multiply here, we're gonna have to multiply there according to basic algebra. So, and this is known as the time independent Schrödinger equation. So now we're going to use this time independent Schrödinger equation. We're going to use this to get another form of the Schrödinger equation, which is the time dependent Schrödinger equation. Let's rewrite it here. Minus h bar squared over 2m plus multiplied by the gradient squared plus, with the Laplacian term, plus v, all of it into psi. That would be equal to e psi. Now if we come back here, let's remember that e is equal to hf. So let's replace that. Is equal to hf multiplied by psi. Okay. From now on, instead of writing this entire term, I'm just going to replace it with the Hamiltonian operator term, which is this, because this is this. Just because it's annoying and it would make it look easier if I just stick to h. So h psi is equal to hf psi. Okay, let's do something random. Let's do h times 2 pi over 2 pi, which is 1, multiplied by f multiplied by the wave function, which, let's remember that h over 2 pi is h bar, and 2 pi f here, 2 pi f is the omega term, the frequency vector. So omega psi. But the name of this equation, or the product of what we're gonna get, is the time dependent Schrödinger equation. meaning that we have to have a time term somewhere. So, but it's time relative to, oh my god, true relative. We can't just put time somewhere there. It has to be related to the wave function. So let's come back, and we see that psi is equal to e to the I kx minus omega t. This is a time term. So we're gonna have to differentiate it with respect to time somewhere. Let's do a little something on the side just to clarify it. We have to put a term here because of this, and we want the time part of it has to be something multiplied by this. Okay, now let's do. Now we're gonna do the thing on the side. Okay, so psi is equal to e to the I kx minus omega t. So the differentiation of psi with respect to time would be equal to I multiplied by minus 1 multiplied by omega minus I omega times e to the I kx minus omega t. This is I got that from a basic rule of differentiating with e to the x terms. You should know this. It's a basic part of calculus. Okay. So we have to find a way to make h bar omega multiplied by psi equal to minus I let's call it x now. No, let's call it, I don't know. Let's call it n. We're gonna have to find n now. So n multiplied. So h bar omega psi is equal to n multiplied by minus I omega times psi. Let's divide psi by both sides, and we get that. Let's forget about psi for now. We'll put it back later on. H bar omega is equal to n times minus I omega. Okay. So what do you have to multiply by minus I omega to make it h bar omega? So if we multiply by I, let's say n is equal to I, is equal to I, n is equal to I, we get that h bar omega is equal to minus I squared omega. It is not, because that would mean that I squared, so omega. So now, what do you have to multiply by omega to get h bar omega? If you multiplied by h bar, it would be equal. So first of all, we multiplied it by minus I, and then we multiplied it by omega, by h bar. So that would mean that, let's write it again, h bar squared over 2m multiplied by the Laplacian term plus v into the psi is equal to, what did we multiply it? What's n? N is I times omega multiplied by the differentiation of psi with respect to time. This is known as the time-dependent Schrödinger equation. Thank you.